Welcome to the pre-recording of lecture 11, the first part of the sixth session of the 8-week summer course of MCS 260. So in this lecture we introduce loops, a very important control structure. But before that we continue our exploration of the computer as a synchronous binary digital system. So in particular, we will see how to compute, how to define adder circuits via logical expressions. Okay, half adders. So what does an adder do? We are adding bits, so looking again, so recall from last time that flip-flops are the elementary electronic circuits that store bits. So let's now start computing with them. So what does a half adder do? It will take 2 bits on input and it will compute 2 bits on output. The first bit being the sum, the second bit being the carryover. So if you are adding up 1 and 1 as 2 bits, then you get the result 1, 0. 0 as the sum, 1 as the carryover. So you see this here, so the carryover is just the AND. So in some sense, the second output is actually much easier to compute. That's why actually the carryover, which we logically, when we add things, it's the second thing that we compute, but the carryover here is easiest to compute. Then what we have to compute as the sum, logically, if you think about this, we have 1 if there is either a 0 for the first input, a 1 for the second input, or the other way around, if there is a 1 in the first input and a 0 in the other input. So actually the formula for the sum is actually the logical definition of the exclusive OR. So either this or that, but not at the same time. That's adding up 2 bits. Once we have the formulas, once we have the logical expression, we can draw the circuits. So the knot is represented by a triangle followed by a small empty circle. Then we have the AND operation. So you see 3 ANDs sitting in there, and there is 1 OR for the sum. So the inputs bits B1 and B2 are passed through the knots and the 1 AND for the carryover. Okay, the next step would be to rewrite this doing a not AND and a not OR, because we've seen in an earlier lecture that the not AND and the not OR are the 2 other fundamental realizations, are the 2 basic operations that are realized by transistors, either putting them in series or in parallel. For this course, what you would, so it's good to know these, so these are excellent exercises, but what is actually most important is that you can translate from the circuit diagram into the logical expression, and also that you can make the truth tables given a logical expression, so the truth tables that were at the previous slide. Okay, so how do we now make an adder circuit? So we have the adders that give us the sum and the carry over. So if we sum 4 bits, then we have the adder circuits. So there is the add C. So the add C is a kind of an extra add that takes 3 inputs. So we are summing not only the 2 bits A and B, but also the carryover from the other uh, edition, from the previous edition. So the half adder, so probably now it is clear why it is called a half adder, because it only this half adder will only work in the case where you start adding up the first bit in your number when there is no carryover yet. So this is the diagram for adding 4-bit registers. So the adder circuit is here just described what it does. So the realization is not given. There is the carry look ahead. That's a technical feature that allows to speed up the addition. The point, however, is that there are certain operations that run very fast on circuits. So in binary, you can shift all the bits. If you shift from left to right, as is done here at the last line, then actually you're multiplying by 2. Dividing by 2 is shifting from left to right. And actually Python has operations to do this. So dividing by 2 or multiplying by 2 actually goes extremely fast. So that's also an excellent way to make very, very large numbers. You could indeed write 2 star star 100, and most likely your Python interpreter will do this correctly and do the shifting, but you never know. If you really want to make sure, so you use these less than operator, and otherwise to divide you use the larger operator. So when we do the power in Python, we actually should not use the hat, because the hat is actually the exclusive OR. We have the AND symbols and we have the OR. If you want to use the bitwise operations, the bitwise and the bit OR, then you use the ampersand for and you use the vertical slash for OR. So this is indicating that you are doing this bitwise, that you're using the bitwise. So and then you have the NOT operation, which in some sense inverts the bits, or can also be expressed arithmetically as subtracting 1 and flipping signs. Okay, so we are transitioning away from the logical circuits, from the more representation of. So the point is now that we understand why a computer is binary, and go into more the programmer mode. So in many programs we run repetitions, we do loops. At the end of the last session, I illustrated that with the Jupyter notebook, you could repeatedly execute the same cell of instructions. And we did this to build our bit string. And you can that's also kind of nice to get hands-on control the execution of a loop. So we have already seen loops already. So when we introduce lists, so when we make lists, so we used actually the for. So we were using a for loop inside a list. So that's called a list comprehension. Python comes with a very powerful standard library, so it provides abstractions for data structures. And list comprehensions are the counterpart data structure, or the data structure that is the counterpart to the control structure, the loop. So if you are using lists, you are most likely also always using a loop. In a very similar fashion, how dictionaries are the counterpart data structures to the control structure, the if-else. So one of our first complete programs was the computing of balance, the balance of an investment. So here we have $1,000 invested at the annual rate of 3.14. After all, this is a mathematical computer science course. We take 3.14 as our favorite interest rate. If we want to store the evolution of a balance in a list, then we can do this with one line with this list comprehension. So we have the formula that we iterate for the number of years starting from 0. So the range goes from 0 by default until 4. So we are giving 5 in the instruction. So perhaps I should emphasize this. So the 5 is actually here the fourth element. So 0, 1, 2, 3, 4. So the first element is with n equals 0. It's kind of redundant. So when we multiply the balance with 1. So there is a second for loop that neatly formats the numbers, so dollars and cents. So we use the fixed format of our floats, 2 decimals after the dot. In general, for a list comprehension using a range, so actually we give two forms. Either you can use a range or you can use this for x in L. That's also very important to enumerate over all the elements x inside the list. Very useful and very nice, both from a syntactical point of view and also from getting a lot of work done quite quickly. All right, but you may be bothered by the fact that there are two list comprehensions, and most importantly, if you only interested in the current balance, you may not want to store all the list of all the numbers. So using list comprehensions might get quite heavy on the amount of data that you start to consume. So more general, you have the loop instruction. So the flow chart here is actually quite nice. So in general, you have your test, and the general test is, should we continue? If that answer is no, false, if the test gives you a false, then you break out the loop, you stop the loop. Otherwise, you execute what is called the body of the loop. So a loop consists typically of three parts. In the center, you have your test. In the main body, you have the instructions that are executed, and then you have the initialization. So a very important point as well. Often count you count the number of steps inside a loop, like the number of years, and that needs to be initialized. All right, here is the syntax of the while loop. So we have while we are not at the end of our, say we have a fixed agreement for our investment. We're going to do this for 5 years. Then we have the test as long as the current year is less than or equal. So if you want to do this 5 times, then we start at 1, and then as long as the index, so I equals 1 is the initialization, then we are we are updating the balance. Note that there is the I here, so if you go from a list comprehension to the loop, there is no I here. So the thing about the list comprehension is also is that you don't change the original balance, so that remains at the very end. Here actually we each time we overwrite the current value of the balance. We talked earlier about statements, operating command statements. This is an occasion where if you're not very careful, so for example, if you forget to increment the index I, then the condition will never be satisfied and you will run in an infinite loop. Sometimes it might be hard to get out of there. Control C typically does it. In your Jupyter notebook, you also have ways to do this, to interrupt a statement. If all goes wrong, there is the kill statement that you can use to terminate processes in Linux operating systems. I give also the syntax format in the similar on the back as now form. So there are the 3 parts: the test, continue or not, the body of the loop, the statements that you execute, and again the indentation is important. So here by default I'm using 4 spaces for all the statements that are executed in the loop. If you would not use 4 spaces in front of the increment I equals I plus 1, then that statement would not be executed in the body of the loop. And again, you would have an infinite loop. Now the infinite loop is bothering us, and the for loop is actually taking care of that. So the for loop is a loop that you must use when that you're recommended to use if you have a fixed number of terms, so in a fixed number of iterations. So in some sense I introduced the while loop because it's a more general form of a loop, but the for loop is actually a more efficient way of expressing a fixed number of iterations, or a fixed number of times you execute the statements in the body of the loop. So typically you have a counter in a sequence, or also you have for X in a list, or for a key in a dictionary. So the for in is actually a much more general construction than it is here for counter in a sequence. For an element in a sequence works as well. Now, a range is actually a range type. So it used to be that range would automatically expand the list. Now, if you want to make a list of elements of integer natural numbers ranging from 3 till 10, that's the command that you give there. Again, I want to emphasize that we end at 10, but we give the 11. So another option, and you can check this with the help, so you can, if you want, for example, only the odd numbers, you want to list 3, 5, 7, 9, then you can give a third element that is the size of the increment or the step size. You can skip a step, but by default you increment by 1. Okay, so it is also indicates, so the type that is inside the elements is actually an integer type. So you can't really do this with floating point numbers. So that's also a problem, a point that I have to point out. If you are defining loops, then there are variables that are changing. So in the balance, we had the balance that was changing, but we also had the year after year. Uh, if you are doing programming, it's a very good practice, or actually something, it's certainly a good practice to have this mental in mind, that you kind of can predict the evolution of the variables. A state table will show the values for every step of the loop. So we have actually seen already state tables when we did the conversion from decimal notation into binary notation. So we had the quotient and the remainder. What we have in the algorithm to compute the greatest common divisor, we have two numbers a and b and then the remainder. We are going to continue, so this is a great application also of the while loop. As long as the remainder is not zero, we're going to continue computing remainders and we're going to continue reassigning the names of the variables. So we assign the value of b to a, and then the val and b becomes r. B becomes the remainder. You see that there's kind of a shift happening in the state table. That kind of defines the pattern, the progress the um, of the computations. So if you want to guarantee also the correctness and understand again how Euclid's algorithm works, you would have a fourth column in this table that also lists the quotient. And then you can rewrite a as b times the quotient plus r, eventually still in another column. And then you can see that the last number that is not zero in the table, so that's b, is actually the greatest common divisor. So 3 is the greatest common divisor of 60 and 51. Okay, so this almost terminates the slide part of this lecture. Um, so I will show how to do exercise 2. It's actually very good practice to get familiar with the loops, that you actually systematically print out everything that moves, that gets changed by the greatest common divisor. So there are actually three parts in this lecture. So there is the slide part, the Jupyter notebook part, and then there are the scripts that we are running. The purpose of this lecture is that you can do the exercises. Um, so I may come back to this. So the middle exercise is actually a great exercise. So the factorial, you can say it's also a way to make very large numbers. And you may actually find, I'm not entirely sure now right away if there would be a function in the math module that does the factorial. But in any case, so you can implement this with a while loop. So each time you subtract and you multiply, it's kind of important to keep. So it's a good exercise because the formula as it is written there, uh, you see n and you see n minus 1. So when you do the subtraction, you kind of have to be careful not to override n. So it's a good exercise to think about what will you use as a variable, as the names of the variables. You can do this with a while. As long as the number is larger than 1, you will continue. So for example, the last multiplication by 1 you don't really need to do. But you can also say, well, hey, there is a fixed number of multiplications. So it's important to recognize also when to use a while, when to use a for. So fors are typically a lot better if you know beforehand how many operations that you can do. So you do as many operations as the value of n minus 1. Well, you can still do n operations if you multiply by 1, but you shouldn't multiply by 0 at the very end. Be very careful for this. All right, exercise 4 is on the binary operator, the number of bits in any given number. We already know how to do this, so you can apply the bin and then count the number characters minus 2 in the string that contains the binary representation of the number. But you can also compute this in a loop. If we have seen the math module has the logarithm. So you can also do this with the 2 logarithm of a number. That's also another way. But the best way, and for this lecture we've seen the binary operations and we are introducing loops, then exercise 4 is a good exercise for loops. This course has calculus as a prerequisite, and you should have seen Riemann sums in calculus, or the trapezoidal rule. We can compute programs that approximate areas. And here in this case, if we have the quarter circle, we can approximate pi. Not a good way, but it's also a good exercise. I will actually show it. It's a good application of the for loop. Okay, so let me go to the Jupyter notebook I have prepared. And the starting example is the application of the yield and the balance. So with the list comprehension, so I will scroll through this Jupyter notebook for my convenience because I can then make sure that I don't make any typos. You see why the second for on the slides you did not see the output, but here you see that it was kind of inconvenient, the default output format of the numbers in the list. So that's why the string formatting, which is another good point for formatting numbers, and good application here. You see, I'm also placing the dollar sign in front of it. So you can actually, in a format string, before the curly braces, you can actually put anything that you want to print. Now, for loops, we can this already do with list comprehension. Again, the main point of this point of departure is that we have data structures and we have control structures. A list is the counterpart to a for loop. Also, a for loop has an initialization. So there is something that changes the balance. Actually, here nothing changes. The balance will still actually be the same. So this is also a way of functional programming. So we have a tuple on input and we have a list on output. This is quite interesting. But nevertheless, so there are questions that you can't really answer with for loops. And again, I was mentioning that it's kind of inconvenient if you are troubled by the two list comprehensions and also the storing of a lot of data there. Here is the corresponding for loop. Notice that I start at year 1. So I can actually, for convenience, I could have printed out the initial balance and the initial at year 0. But here I'm printing out the value of the index running from 1 to 5, so not 6. So note that the range starts at 1. If you want to start at 0, then that would be wrong for this application here, because in year 0, you actually have not yet an interest. So you have your initial balance. So it's an illustration how you can let your program compute the state table. In a traditional pen and paper exam that we often did in the past, we would give code and then ask the students to compute the state table for every step. Since this is now an open book exam, you should be capable of computing the state table. So one of the questions is that you have a formula, you put it in a loop, so the formula is now in the body of the loop. Notice the difference, there is no to the power I here. And I must confess that when I prepared this Jupyter notebook, I was very sloppy. Actually, I just copied and pasted the formula there. So there is a huge fundamental difference, and this is also why on this Jupyter notebook I have the output from the list comprehension and the output from the for loop. And you can see that the numbers, they agree. So I have 5 years in which the numbers are evolving. So I didn't emphasize this with the previous section, but you have the range 6. So in the list comprehension, I put the original balance still there. So that's why there's only one number in the argument. By default, if there's only one number, then that number is taken as the number of elements in the range. So on the slides, I introduced the while loop before the for. Coming from list comprehensions, one should introduce the for after the list comprehension. To motivate, I was motivating the for actually by the flowchart, and also I was motivating the loops by the flowchart, and also the motivation for the while is that it is a more general loop, and you can ask the following question. So I will motivate the while loop. Why would you need to know the while loop? Well, suppose that I want to compute here with the loop, so you can see that after 5 years I have a yield of $167.17. You could ask, how many years will it take till I get 1500 as my balance, or where I have a yield that exceeds 500? How long do I have to wait on this interest rate of 3.14? Well, you could do trial and error. So you could say, well, instead of 6, I'm going to put 10, and that's not going to work. Well, let's do 16 or do 20. But that's kind of, and then we will see what it is. But you can actually do this in one step, and that's being done in the while loop here. So we have now an initialization that contains the counter for the year. So I'm initializing the index I. I will start at 0 at year 0, which is now. And each time in the loop, I increment it. I add 1 to it. So you see the printing of the state table, and you see that in answer to the original question, we have to wait 14 years to see that the balance is more than 1500. So it's very important. We want to see 1500, but we will continue. So that's actually the general picture that you have in the test here. So we will continue as long as we not have 1500. So you continue as long as not 1500, which is here simply expressed by the condition be less than 1500. So as soon as we have 1500 or higher, we no longer continue the loop. So we have the initialization, the stop test, and then the body of the loop. This is the while loop. So let me continue scrolling through. So in this Jupyter notebook, I have now explained the essence. Let me give two more applications, two additional applications. So we have the greatest common divisor. And actually, there is also a script that is posted. And the script, the exercise is actually asking you for printing the state table. And here you see that I have solved this exercise already. We have the A, the B, and the remainder. And you see the shift that is also happening in the evolution of the algorithm. It's also kind of a motivation for the next lecture, so the second half of our 6-week summer session. So you can see, and so we like short pieces of code, that we're still kind of uncomfortable by the duplication, the duplicate statements. So we actually, and this is here is important. Our stop test is if the remainder is not yet 0. But that's a case where we can't really immediately test on this. So we have to have first a remainder before we can do the test. And the remainder is something that happens also in the main body of the loop. So, and for completeness in the state table, so you should also print out the initial values. So the other state tables are, in some sense, strictly speaking, not really complete. I should actually have also, let me do this more pedantically. So I should actually have fixed this. So the state table should actually have included also year 0. So I should also have had this statement. So this is the complete state table. And also here, so this instruction should actually have been completed. So also at the initialization, I'll actually have also here the state table. Oops, interesting. So I is here, of course, 0, not 14. So that's an artifact of executing the cells in a Jupyter notebook out of order, which would have failed because the I, so very important here. And probably I should document this. It may matter here. So in a for loop, the I in range 1, 6 limits the scope of the variable I. So the scope of the variable I, what is this? So the scope of a variable is the space in which the variable, and now I will use a metaphor, is alive. So that means for which a value, for which it exists. So the statement, so if I would clean, so the statement you saw instead of I equals 0, you saw I equals 14. So, but the I, if I'm running this, so the I will actually has only a meaningful value within this for loop. So you can't really, and I feel that if you could actually use it outside, then it should be wrong. And actually, I'm now I should actually test this. Let me restart the kernels. You see, you can interrupt a kernel. So you can also interrupt a statement. If you ever get into an infinite loop, this is useful. I will restart the kernel and run all statements. So there are not too many statements. So I have not used, so I do Shift Enter every time. There we go. So I'm running these statements here. And what I actually want to indicate is that the I is actually 5. So the I is actually still existing outside the loop. So which is kind of unfortunate. So typically the I should actually only be valid inside the loop, but it's still valid outside the loop. So the scope in which it's meant to live is within the body of the loop, but it lives actually on outside the loop. So let me document this. The intended lifespan of a variable I in range, so 1, 6, is only for the statements inside the loop. But we see that the value exists, and thus I exists, and thus also after the loop. So scope is important. It's an important concept. I will get to this also in the next lecture. Okay, so let me execute everything again. So here you see the I. So the I is here reinitialized. So if you forget the initialization, and in some sense our Jupyter notebook is one long program now, then actually you get very strange things happening. So, all right. Here is the state table for the greatest common divisor. And I will end by showing the application coming from calculus. If we want to estimate or approximate, not estimate, if we want to approximate the area under the 1 minus the square root of 1 minus x to the power 2. I need to have the square root. And now this is hard to explain without a picture, but you can see, so there are several things that I have to explain. So we have the interval 0, 1, and we divide this here into 1 million subintervals, so our computer doesn't mind doing that. So the capital N is 10 to the power 6, so 1 million. So all the points are 1 over n. So in here I explicitly, so the I is an integer, and I explicitly wanted to have the floating point division. So in a former version of Python, this was really critical to see I as a floating point number. So, but now it's no longer critical. But you see two consecutive points, and now here it's also interesting, we go from 0 to n minus 1. So I compute x to the power x1 to the power 2, x2 to the power 2, and I have the base and I have the height. You see, each time I'm computing the area of a very, very tiny trapezium. So, and I'm added up. So base times height. The height is actually the average height of the two function values. And you see that It went instantaneously and should also be instantaneously on your computer. And we have about 9 decimal places, correct. All right, this is almost the end of this lecture. So in the past, I dumped everything on slides and then I had additional Python scripts. The Jupyter notebook now functions a little bit as an intermediate representation, as kind of an intermediate uh, functioning between the slides, the concepts, and the actual scripts. So the scripts are actually what we really care for. So I have several scripts prepared. So here are they. So there is so I can go quickly to the the showing of the balance. So we had this very early on program computing the balance of an investment, where the formula was the end balance and the yield was listed. Here you actually see in every year the balance. And this is still done with an old formatting string, but let me run it anyway. So you could, so it would be better for me to rewrite this using f strings. So 100 now at 3.14 for 5 years. So here you see the evolution, and in some sense it's nicer formatted, but you see in some sense again the state table. We can also do this with a for loop. So here you see the better program actually with a for loop. So the programs are interesting is that they are more variable. So here I have the prompts. So the user is prompted for the number of years. So this allows me to figure out what is the end range here. So I have to put n plus 1. So that's why actually why I was a little bit doubting between the 5 and the 6 here. But logically, you may make sure that it corresponds to what the user intends, the number of years. So you have to execute your loop as many times as the number of years, and therefore you put n plus 1. So these are very simple programs. A little bit more interesting is the greatest common divisor. Um, so I wrote the exercise starting from the Python script, where the exercise is here including the print statements for the state table. So that will compute the greatest common divisor. Again, I have not used the format string, so this is a little bit my exercise here. So this is the other, if you like, the alternative way, other than format strings, how you can place values into strings, into decimal notation. So these notations here. Okay, so then the last program is the trapezoidal rules as a program. Okay, so I would invite you to run these 4 programs. They are posted at the website. So the Jupyter Notebook, also look at this. The Jupyter Notebook allows you to experiment with the programs as they are assembled. So the difference between the programs, the main difference here is the prompt at the beginning. That allows us to parameterize the number of times the body gets executed. So now the number of times we execute is really fixed, is really variable. So that is determined when the program gets executed. Okay, I hope this was interesting. In the second part of the session, the next lecture, we will introduce the break statements and see many more examples and applications of loops. So in this session, we kind of terminate, we kind of have the most important parts on the control structures and the data structures. What then follows are functions. So the programs that we are currently looking at are very small. You do not need functions. But when it get to larger programs, functions will be needed. Okay, I'm again running over time, so I'm stopping here.